Hello class, today I'm going to show you how to deal with contact. This time we're not going to have any force, and the stress or force is going to be created by overlap between two geometries. Okay, so let's start. Okay, everything is ready. Let's open static structure and define materials. I have static structural structures as a default material. I want to have a softer material. Let's see what I can find. Yeah, polyethylene is going to be good choice. It's softer than steel, and I'm going to crash it. Okay, now we have two materials here ready for our selection. Let's open geometry. Okay, what's the plan? I can draw a large geometry for a stiff material and a smaller geometry for soft material, and have a little bit overlap between the geometries and create force. Because I'm using 2009, the free version, so I'm going to limit all the sizes to be able to use as minimum as possible mesh number. So our stiff geometry is going to be a pipe, 20 millimeter internal diameter, and external diameter of the pipe is going to be 22 millimeters. So 1 millimeter thickness of the steel pipe. Let's extrude this. Yeah. Let's go with 30 millimeter. So the length is going to be 30 millimeter. As you can see, we have a surface automatically generated when we draw 2D. So I'm going to use that one too. So let's move and create a pipe. And now it's time to create insert material, which is going to be a polymer. So I'm going to select the surface at the end, automatically generated, and pull it about 20 millimeter. Okay, the diameter of the inside or insert material is exactly same as pipe. Let's create some hole inside, rectangular hole inside, to make sure we have area, the highest stress area. Basically, I'm creating weakness to my insert material. 12 millimeter by 10 millimeter would be good. Let's cut it. As you can see, we have a lot of 4 sharp edges inside. Sharp edge means we need to have more mesh, and the accuracy is going to be important around that, so I'm going to get rid of those sharp edges. Let's select all the edge using Control key. Now let's drag it. It's a round, so if I drag this, I'm going to have round edges. 1 millimeter is going to be enough. And still, I'm expecting to have stress concentration about that corners. And let's name this polymer as an insert. I haven't changed the diameter of insert, and it's exactly same as internal diameter of the pipe. So I need to create overlap. Let's hide pipe, and I need to click over pull to be able to change the diameter. It's currently 10, radius is 10, and the diameter is going to be 20, exactly same as internal diameter of the pipe. So I need to be a bit large, make it a bit larger. So 10.1 millimeter is going to be our insert diameter. So about 1 millimeter radius, 10.1 millimeter radius, and 1 millimeter is going to be overlap. Okay. Let's bring back pipe, and let me check if we have overlap or not. Yeah, we can see the overlap there. It's about 0.1 millimeter. Okay, let's start with analysis. Okay, it's ready. This is our geometry, and we can see that there's an overlap between insert and pipe. Let's check the material for the geometries. The first one is pipe, and the material is structural steel. The second one should be softer one, polyethylene. Let's see, no connections here. Usually when the overlap is very small, ANSYS recognizes and automatically generates connection, but I'm going to generate right now. Let's select the surface, the internal surface of the pipe and external surface of the insert. As you can see, I highlighted those two lines which are going to be our contacts. Let's click contact, and I want to have frictional contact. We have several types of contacts here: bonded, no separation, frictionless, frictional, and rough contacts. And they're going to have different applications. Okay, let me show you some specification of these contacts. Frictionless contact, as you can see, we have contact over target. Contact is the black box, and no separation. Separation can happen for frictionless, and slide also can happen without any resistance. So this is frictionless contact. For frictional contact, again, we can have a separation, vertically separate contact and target, but for sliding, it is going to have some resistance, which is the friction coefficient, and it is going to be depends on the normal force. Rough contact, again, we can separate the contact and target, but we can't slide it. And for no separation, as it comes from name, we can't separate contact and target, and it can slide without any resistance. Finally, the bended contact, which is going to be everything is going to attach, no separation, no sliding, and we work a lot with bended contacts because it is like a welding two geometry to each other. And here we have our contact. The soft one is a red one, which is our contact. The blue one is the stiffer one, which is our pipe, and it is a good arrangement, and we expected, and automatically ANSYS selected those for us. This is frictional contact, and I need to specify friction coefficient. I can select behavior, and as you can see, we have asymmetric, symmetric, and autosymmetric selection. Depends on the stiffness of the materials. We can select one of them. Let me show you something here. As you can see, for asymmetric, we usually select when we have flexible bodies. Asymmetric, flexible, rigid body, autosymmetric, flexible body, and symmetric when we have flexible body that are scoped to a nonlinear adaptive region. So basically, when there's a big difference between stiffness, one of them is flexible, the other one is rigid, usually go for asymmetric. And if you were interested more and had a project about that, you need to read exactly the definition of these selections. Okay. Also, we have several formulations. I'm not going to change these formulations. And regarding interface treatment, I want to select add offset and ramping it out, because I want to have originally overlap, and then at the beginning and during the simulation, ANSYS is going to get rid of this overlap. So it is going to be add offset and ramped effect. Gradually, that offset is going to be removed, and force is going to be generated because of removing that offset, the initial overlap. Okay. Let's see what's the next step. Let's generate mesh. First, default mesh. Not very good. As you can see, we have one layer of element for the whole thickness of pipe. We need a bit more, and I need to take care of this part. Let's select the surface of the pipe at the cross section, and then do face meshing. 3 would be good. Let's update. Now we have more elements at the thickness because we want to see what's the stress and gradient of stress inside the pipe. Let's improve the insert material. Sizing could be better. Let's start with 2, for example, 2 millimeter. If it wasn't good enough, we need to decrease it a little bit more. No. 1 millimeter. Okay, much better, and I'm happy. As we expect, these corners are going to have stress concentration, and that is, if we need it, you need to locally uh, improve the quality of mesh about those rounded surfaces. Let's go and apply some support. I'm selecting those two ends, and frictionless support would be good. Yeah, so I applied support. We already have overlap, so it is going to create force. For the analysis, I'm going to specify some steps. I don't want to force be applied all of a sudden, so I have smaller steps, 20 initial, minimum 10, and maximum sub steps 10,000, for example. Let's turn on large deflection and weak spring, because if I don't turn on weak spring, it is going to slide, the whole geometries are going to slide over each other, and I don't want to have that. So I want to have a much more stable simulation. Okay, the simulation is already ready, almost ready, and I need to add a few solutions. Yeah, one is a stress, strain, total deformation. Also, I can add safety factor, because I want to see what is the safety factor range for the materials, which one is going to break earlier, and solving the problem. Okay, my license doesn't let me have enough mesh, so I'm going to get rid of the mesh for inside. Oh, still it's not low enough, so let's decrease the quality of mesh from 3 to, for example, 2. Let's 25,000. Hopefully 25,000 would be low enough for this license. Let's solve it. Yeah, it is doing it. And let's watch the force convergence. As we can see here, we have two colors, purple and blue. Purple is the force convergence, and blue is the force criteria. We always expect this purple line to be under blue line to converge. At the early stage, it was above that, so ANSYS is going to solve more implicitly, try have more sub calculations to converge. For example, at that point 4, we reached that point, and up to now we simulated 0.1 second of the total 1 second simulations. Again, ANSYS trying, it jumps up above the blue line, which is the force criteria. ANSYS tries again to converge and take it lower. When the purple line is under blue, we have progress in simulation time. If you check each time that line goes under blue line, the time here is going to increase. Right now it's 0.2. Next time it is going to be, for example, 0.3 when we converged. Now it's time to move. Remember, we had these three contact types. The first three is going to be nonlinear because we have separation. The last two are going to be linear because we have just attached, those objects are attached to each other. So for first three types, we have nonlinear solutions. That is why ANSYS tries to converge for each iteration. We can't progress in time till reaching convergence. That is why here ANSYS, for example, trying to converge, still it's not under the blue line, the force criteria. Now it went to under blue line, and now you are going to see this time is going to increase from 0.3 to 0.4. Again, it jumped over blue line, and this process is going to repeat and repeat and repeat. There are occasions ANSYS tries very hard, but can't converge. After a while, it is going to tell you, I can't converge, change something, improve mesh, or the time steps should be, the sub steps should be smaller, and you need to edit to help ANSYS to be able to converge. Up to now, 0.6 second simulation is ready. Hopefully in a few seconds we are going to reach 1 second simulation. Point 0.8. Next time it is going to, when it converges, we are going to reach 0.9 and then 1 second. Yeah, converged. Let's see, it is going to be 0.9. Yeah, 0.9. And next time simulation is going to finish. Now ANSYS just prepares the data for us to evaluate the results. Done. Equivalent stress, as we can see, pipe is going to have some stresses over it. There's a large gap between the inside and pipe. It's because it's not true scale. Now it's true scale, and we don't have any gap between them. And interestingly, about the corners which we created, pipe is going to have higher stress, 176 megapascal, exactly close to the area we had the round corners of inside. Okay. It's like a repeated 4 times. We could do this simulation for quarter of this pipe, but I wanted to show you the whole pipe and it would be easier. Let's see, the insert material is going to have much smaller stress. Let me increase this. See, it is about 40 megapascal for that corner. Again, if we check strain, the insert material, polyethylene, is going to have much more strain, and maximum was in the corners. And for the deformation, total deformation is not, interestingly, it's not symmetrical. And at the lower part, we have more deformation than the upper part, and we need to investigate. Maybe if we had a finer mesh, the symmetry would be more. Yeah, okay. Let's hide one of them, for example, pipe, and check stress. No stress at the top outer surface. main stress are all at the corners we created, so it is going to break from those corners. So if I check the safety factor, yes, as you can see, the lowest safety factor is going to be for the insert material, and exactly at the corners, 0.5. So by pressure fitting the polyethylene inside that pipe, it is going to start breaking and cracking from those corners, and we're not going to have that much life for that material. And but for the pipe, based on these colors, I can see it is about like the safety factor about above 3, which is good enough. So the weakest part of this design is going to be for insert material. Okay, more details. By the way, if our material had a SN diagram, you could check the fatigue calculation for them. So if you were interested, add a SN diagram to your material and investigate how many times you can push pressure fit that elastomer inside that pipe. It can be interesting. Okay, thank you very much, and see you next time.